Okay, welcome. So we have 4 talks before the lunch break. The first one is in Arabia Terra, and I'll do my best Vanna White.
Not very good, man.
Not very good, yeah, okay. The first talk is from Nicolas Mangle, who's in Nantes, France, and he is online and presumably ready to go. The talk is about Ismenias cavus, ancient lake deposits and clay minerals surrounded by Amazonian glaciers. So a little bit of everything. Nicola?
Okay, thank you, Matt. Sorry for not being able to come in Houston. So I will present this potential learning site in Ismenias cavus. As you can see on the topographic map to the left, Ismenias cavus is located just south of Deuteronilus Mensae. That is the region which was presented by Jeff Plott and Jim Ed just earlier. This region is located 33 degrees north, so it's an interesting region because it shares the presence of mid-latitude ice deposits from the south of Deuteronilus Mensae region and some clay minerals which usually are observed more in the equatorial regions, and those one are one of the highest latitude clay minerals observed. Other interest in this ellipse, in this interest zone shown to the right, it's the cavity. Ismenias cavus itself is 70 kilometers where I put most of the region of interest. And you can see to the southeast of the cavity, this valley is called Mammoth Valley. It's a big Noachian valley that went inside this Ismenias cavus trough. The cavus itself is a big trough. It may have been a crater once, but it's probably due to a lot of collapse. And there is a lot of interest inside, as we can see. Not much on this topographic map to the left, but it's just to show that we have a HRC map with most of the interest lying inside the 70 kilometers diameter trough. And now this is a geological map that has been done by De Hoek, one of my former PhD students. It's published in Planetary Space Science in 2010. It summarized all the interesting landforms we have in this region. So I won't detail all the geological map, but just show some of the most interesting features that are observed in this location. And starting with dark blue areas, there are big one to the south, which is at the edge of Mammoth Valley's outlet. And this is there are a lot of deposits with some fluvial bars going inside this Ismenias cavus trough, and it probably corresponds to fluvial and deltaic deposits due to this fluvial location. So now when you look to the 2 other bluish area on the geological map, those are also small fans which have been interpreted as delta fan even in the past in a paper based on Viking images. And with the topography, it's still present a flat plane at the top and the front, which are both consistent with the presence of a delta fan here. And what is interesting is that these 3 landforms in dark blue are all at the same elevation. So it's consistent with the coeval activity from a past lake at an elevation which is around 3.1 kilometers below the datum. So there might have been a paleolake in this cavity, in this big trough once in the past. And one of the big interests which triggered our curiosity several years ago is that we observed the phyllosilicates in this location based on numerical data. So on this early data, we just show, we had very few images at that time, and the data were located on a very dark area, but actually the area is just darker than the surrounding, and it's a kind of window inside more dusty places. And the phyllosilicates which have been shown from Omega, are now mapped with cruising data. So again, in the same paper by De Hoek. And when you see what you see on the cruise map to the right, what is purple is a combination of two absorption bands, one at 1.9 micron, which corresponds to water absorption, and one at 2.3, which is typical of iron-magnesium OH bond. So it's typical of iron-magnesium phytosilicates, like smectites, fits best here these deposits. And they correlate with an erosional window of sediments at the lake, at the bottom of the trough, at the bottom of Isthmianus cavus, which is just in front of the big deposit from Mammoth Valleys. So very interesting location with clay minerals. And if you look to the interior of this location with clay minerals, what you can look is a lot of very thin layered materials consistent with the interpretation of fine-grained layered deposits, possibly formed inside the lake during the lake activity, and full of clay minerals based on spectral data. And clearly this is also the science objective and the science region of interest number one, based on these observations. And the proposed landing sites, whatever it will be of real size, it could be just nearby because all the terrains just north of this region 1 are relatively flat and accessible. So now I'm going to present the second type of region of interest. I have grouped the region of interest by topics and by decreasing order of interest. And so the second interest here are clearly the glacial deposits which are on the edge of Isthmianus cavus. On the map to the left, they are all mapped in the light color with small arrows which indicate flow directions. You can see we have a lot of these glacial features. And to the right, you can see a context image with the glacial front. And this texture, this type of morphology is very typical of low bay debris apons as shown earlier by GMAT, for instance. And those ones are located just 10 kilometers east of the landing zone and of the region of interest number 1 in the clay deposit. So very close together. Just a small close-up of one of this region with ice. It's a pitted texture. It's typical of sublimation of ice, and you can find the same texture on most of the glaciers all around the place at the Deuteroninus. So those glaciers are those which are the most to the south from all this region. And on the other side, to the west, so the region 2B has also a lot of glacial landforms, and you can see the glacial front on this context image. So we have a lot of ice on both sides of Isthmianus cavus all around the place. Now, as a region of interest 3 and 4, we can focus on the rest of the story of the fluvial and lacustrine deposition, especially by going upstream on the delta deposits. First, if you look to the image the most to the right, this is an IRAS close-up. You have a light tone layer. This light tone layer shows still clay minerals. And then you can climb inside the front of the deposits. The signature with Planetary is less clear, so it's probably dusty, except where it's dark, it's covered by dark sand. And where it's dusty to the south, we don't have any more signature, but it's still layered deposits which are part of what we interpret as a delta deposit from Mammoth Valleys. And when you are at the front of the deposits, you can see some fluvial bars showing a fluvial incision inside the deposit, which are also of interest to reconstitute all the history of the lake and the Mammoth Valleys activity. I put a fourth region of interest, which is more upstream. I think it would be of interest to go upstream inside Mammoth Valleys, but that's further away, and it will be easier to first analyze what's immediate in the surrounding of the center of Isthmianus cavus. Now, going to another type of science interest in the region 5. On the geological map, it appears in yellow. That consists of rougher terrain, looking like ejecta deposits of this crater, which is to the north, at the northwest of Isthmius Cavus. And these ejecta may be locally covered by ice, as is the case where it's looked to be smooth here, for instance. But these ejecta are interesting because they will excavate rocks from the Noachian. All the rocks around are Noachian islands, and so these ejecta will enable us to dig into the Noachian crust, and even it's partly covered by Amazonian blanket of ice and dust. There are some locations like this hill, which probably display boulders coming from the Noachian. So we have access to the crust in the vicinity of this landing zone as well. So to summarize the scientific interest here, we have a range of geological time going from the crust with possible sampling of the crust to the aqueous processes typical of the late Noachian early Hesperian history of Mars with potential past stability and a good preservation because some of the sediments showing clay minerals are recently exhumed. And so what's also interesting is that probably the Isthmius Cavus formation date during the Noachian, but we have a good constraint in age with Cerulli crater, which is a crater that has been dated as 3.2 gigayears and which post-date Mammoth Vallis. So all the aqueous activity takes place into this period. And now we have also the glaciers, which are more Amazonian and which display probably present ice, as is the case in many locations around Neutronilus. So for the resource, it's very short, in very short time. The first is also the first resource region of interest is the same as the science interest in the clay deposits. If it is saponite, which is the best fit, it can contain both hydroxide and water. And the second region of interest corresponds to the glaciers with ice close to the surface. And what I did not say yet is that there is a region around the number 3, around the third region of interest right here, where we can observe a lot of darker areas. And these darker areas contain dark sand, typically rich in pyroxene in spectral data. And this may be also accessible very close from the landing area and could correspond to mobile material good for construction. So to summarize the sources, so the key message is that we may not have to choose between water ice or clay minerals. There are regions on Mars where you can find both at the same location in very close, in the very enclosed area of a potential landing site. So these are the rubric. I try to feel that I don't know if I need to go through. I think you can check, and from what I say, that it's we have some threshold for past habitability, at least with the clay minerals. The rubric for the resource, again, it's ice and clay minerals. And so to summarize, some imagery would be nice to get on the glacial flow, especially there's not that much images compared to other locations on Mars. But anyway, what's interesting to me on this site is that it's one of the few locations on Mars where you can find both present ice with low bay debris ponds and past lake sediments with clay minerals, which should trigger some interest to this site for future exploration. And thank you a lot.
Thank you very much, Nikolai. We're going to hold questions after the next 3 talks, so if you can hang around, that's great. Let's see, our next talk, we're going to go back to Eastern Hellas, and we're going to look at an area called Mesopotamia. Is that better? And the speaker is Gallegos, and Newsom is an author as well. Just like that.
Okay, so first of all, I'd like to thank everyone who's putting on this meeting. It's really fun. I like it a lot. Also, I'd like to thank my co-author, Horton Newsom. And my name is Zachary Gallegos. I'd like to tell you about a little site in the eastern part of Hellas that I've been referring to as Mesopotamia, just to distinguish it from the other sites over there. And I call it that because it's between these two, or three actually. What's that? Okay, gotcha. Between these three valleys over here, you got Niger Vallis, Dow Vallis, and Hamarcus Vallis right here. And we're going to be zooming in on this area right over here. So here are some of the major geologic, or the features in the area. You got Hadriacus Mons, Gander Crater, Dow Vallis, Niger Vallis, and a few of the craters inside the EZ, Q Crater, and Nagelle Crater. And here's a close-up again, and showing the areas that could be good for the landing site and the habitation zone. The landing site area, this is a large area that's very flat, and the habitation zone is also relatively flat, very few craters. And here is a broad geologic context from Tanaka et al. And you can see we have a few different sorts of units in here. Mainly we have the volcanics, the late Hesperian, the early Hesperian, Hesperian volcanic edifice, Amazonian Hesperian impact, Amazonian Noachian apron unit, and some outside the highland massifs. And also overlaying the remnant magnetization, so you can see we might have an opportunity to sample the old magnetic. And okay, the exploration zone. Here you can see the ROI is mapped out. ROI 1 down here, 2 up here, and everything like that. And so the science ROIs. Science ROI number 1, Amazonian Noachian apron unit. And it's not just one little deposit. I could have said that each of these were a science region of interest, but you got 1, 2, 3, 4 different big glacial deposits that you can look at. Possible, not really possible, but Amazonian water ice, aqueous processes, Noachian bedrock, possible remnant magnetization, and you've got also a few impact crater features over here. And so we have potential for past habitability, although it's low. You got Noachian trapped gases, meteorological diversity, range of datable surfaces. You can get some till off of the Noachian Highlands Massifs units. And let's see. Science ROI number 2, Niger Vallis. There are areas in here inside the EZ that you might not actually be able to reach with a rover. And the EZ can be moved a little bit if we want to exclude those areas. But I was thinking we could actually drive a rover up into here and maybe access this little basin right there. And the rubric over here, just about the same as the last one. Potential for past habitability, although low. And aqueous processes, igneous rocks, mostly the Hesperian volcanics. Science ROI number 3, Nagelle Crater. So you got impact deposits, possible trapped atmospheric gases within the ejecta, and also water ice inside the crater. And the rubric, again, some potential for past habitability given the ice and the impact, possible hydrothermal. Trapped gases because of the impact deposits. And igneous rocks, possibly the Hesperian, maybe the Noachian. I'm not able to see actually if these if this crater imprinted over the Highlands Massifs or if it's more on the Hesperian volcanics. So now the Hesperian volcanics units, we've got igneous rocks with plenty of ridges in here, lots of datable surfaces, trapped gases, and impact deposits right here, Q crater, and this one up here near the habitation zone. And the rubric for this one, you got trapped gases of Hesperian age, datable surfaces, aqueous processes. You can see these channels flowing through it right here, impact deposits. And same thing up here. this unit extends to about right there, and so we'd be able to access this area right here, and the EZ comes about right in through here. So you get this little corner of this unit right there. And again, just like the last one, aqueous, maybe some subsurface ice, datable surfaces, igneous rocks. And so here are the rubrics. So we've got some potential for past habitability. You've got Noachian and Hesperian rocks, trapped gases, lots of datable surfaces, and lots of other stuff in there. So now to the resources. You've got the Amazonian glacial ice around these highland massifs, and you can also use the glacial till for, civil engineering sorts of purposes. And the rubric, potential for ice, I'm not sure if it's less than 3 meters, could be. And also, depending on where we put the processing units, it could be within the 3 kilometers range. Let's see. And Niger-Vallis, also potential for water ice in those lineated valley fills, hydrated minerals also. Potential for ice, hydrated minerals, possibly. So Nagella crater, we can get some of the impact glasses possibly for processing and using for silicon. Also the water ice, we might be able to access it through this area right here. And the rubric for that one also. So the volcanic units, I'm not sure if we're going to get a lot of ice out of there. You can see some of these craters could have ice deposits around them, but what we can get from those are cobbles and regolith and other things that we can use for civil engineering purposes. And take a look at that if you want to. And again, for the late Hesperian, you got cobbles, rocks, regolith, and maybe metals. You never know what we can do in the future. And here's the rubric for the resources. So you can see we have lots of ice in the area. Potential for, or not potential, lots of regolith, lots of cobbles, other things we can use for resource. It's not low latitude. We do have access to water. It's not in the northern hemisphere. And let's see what else we have here. Okay. So here are the entire site rubrics for the science and the resources. So potential for past habitability, albeit low. Noachian trapped gases, Hesperian trapped gases, possibly. Range of Martian datable surfaces. Evidence of aqueous processes in the form of those outflow channels and also below those glacial deposits. Igneous rocks and near surface ice. Outcrops with possible remnant magnetization that we might be able to sample. And potential for water ice. And we do have this large area for our habitation zone and landing zones, so that shouldn't be a problem. So this is the current horizon chrism data. We have not too much chrism in the area. We've got one little spot right there inside of Dow Vallis. Probably not accessible, so we do need lots of chrism data. And mostly we need lots of high-rise within probably the landing zone and the habitation zone. So looking at some of the high-rise and chrism data, we can see the Noachian Amazonian apron unit and these craters that are overprinting it right there. And bound water within, this is an area to the south. This isn't the chrism for my area because there are no chrisms for the for this unit, but just showing what it could look like if we did have it. And some high rise from inside Nagella crater showing these gullies and possible water ice in the middle. And a crater near the habitation zone also has some high rise around it, so we can look and see what we can find around there. And also some high rise over in Niger-Vallis. And it looks like if the rover drivers were brave, we could get down here maybe and look at this possible closed basin. And some more high-rise to the west in Niger Vallis. And also that chrism spot down here showing some bound water. So the easy science data needs, we need orbital data, high-resolution imagery, high-resolution spectroscopy, and a possible rover so we can do science reconnaissance, MSL class or better. For the resource, we need a rover to go to these ice sheets. We need it to look at the impact glasses and scout for possible metal resources. We also need orbital data for looking at the spectroscopy and of the ice deposits, and more radar possibly for seeing what those deposits look like. And for engineering, we also need high-resolution imagery because we want to confirm the landing site as possible and look at our traverse capabilities and also rock abundances. So one thing that was mentioned earlier is rover teleoperations, and I think we should all consider this because it gives the astronauts something to do while on Mars. It's faster and more capable than, say, the Earth-based operations. And it increases the EZ radii, giving you more science potential. And so here is the 100-kilometer radius, and here extending it by 50 kilometers, and then another 50 kilometers to eventually 200 kilometers. And you can see we get a few more geologic layers in here. You get the Hedriacus Mons and the Massif units, and lots more datable surfaces within the volcanics. And that's it.
All right, excellent. Our next talk, we're going to move north to the Uzboy Vallis drainage, hail craters. See if I can do this better. Okay, and our speaker is David Stillman.
Great. All right, thanks for having me. All right, so my motivation for writing this abstract was really just reading through the supplemental material and seeing this giant football field here, talking about mining a football field's worth of hydrated materials. And being an RSL guy, being very excited about these RSL, these recurring slope lineae, it was just, why not go to this natural Martian spring that we have? Let Mars do the melting for us, and let's just pipe this, aqueduct it back to the HAB. Also then, later, about a month ago, during the big RSL press conference, Grunsfeld was asked what to do with the RSL, and what did he say? Drink it. So I'm kind of following that path. Here are all the RSL here on Mars right now. We've got 200 confirmed and candidate sites. They're color-coded here. White would be, we've got 1 or 2 images that are showing RSL-like features. If they're blue, they've got one of these 3 characteristics of an RSL. And then if they're red, they've got all 3 and they're a confirmed site. And we've already got 51 of those, and we just keep finding more and more. This is up to date as of the last high-rise release. So now it's just going through the different regions. Up here in Crissy and Acidalia, we've got a lot going on in here right now. But these are all in pretty small craters, 1 to 7 kilometers in diameter. And there's no way, unless you're rappelling astronauts down, that you're going to be able to access this water. So those are out. We've got Vallis Marinaris. You could definitely get to the RSL here on the side of these cliffs. Just walk up to it. But the problem, I think, is it's really tough to land here with all the winds and everything. So I had just kind of thrown these out. And I hope that we actually can land here. And we could use those resources. It'd be a lot easier if we did it closer to the equator. Tropical mid-highlands, or tropical highlands here. This is kind of the newest region on Mars. We've got 3 confirmed sites now, but these are all in these craters again, so you're rappelling down. Not a good idea. Here's the southern mid-latitudes. Here we actually have some craters that are very big, like 100 kilometers in diameter, and we see the RSL coming out of the central peaks. So you could actually land in that 100-kilometer diameter crater and go up to the central peak. So this is, we picked Hale. It's one of these. It's also got a lot of other exciting things going on. First of all, Hale, which is right here, is on the rim of Argyre crater. So this was a significant stratigraphic event. A giant impact happened here about in the middle Noachian, almost 4 billion years ago. And many of the features around here are all mapped on the ejecta, mapped relative to Argyre. So if we can actually date when this happened, when Argyre happened, by being in Hale here, looking for some shock quartz, that's going to really help cement in the whole Martian geochronography. Then also this happens to be on the Uzboy land in Morava Vallis, the outflow system. And this transported a lot of water back in the late Noachian to early Hesperian. However, the source of this is really unknown. It's some people think it's over here, some people think it's Argyre overtopping. And Hale is a relatively later crater. It happened in the Amazonian. The floor has actually been dated to 1 billion years, so we know it happened at least 1 billion years ago. And there's this great geologic map by Jones et al. Talking about this fluvialized ejecta that modified channels. It occurs over a very large area here. This is similar to Mojave crater or Tooting crater, so this isn't the only place, so we could go here and learn about what's going on in these others. This is just an example of this ejecta coming in, filling up a crater and then flowing back out the other side of it. And so there's all these channels all around. And it's been estimated by this paper that this impacted melted 10 cubic kilometers of subsurface ice back in the Amazonian or so. So this is telling us about water in another time frame of Mars. But right now, when you're trying to figure out where to land, you want to land right next to your resources. So let's look at where the water is now. This is in the central peak of a Hale crater here. This is a CTX image. I've got the high-rise images that we have, the coverage. So we've got really good coverage here. And what we're finding is RSL are very dense right along this central peak. We've got a little bit of RSL activity going on up here. This image right here had no RSLs in it. I think if we shift that over a little bit here, we'll probably get some RSL. The RSL really like the warmest facing slopes, the northwest and west facing slopes for sure in this area. And so where to land? This is actually a flat kind of, there is a flat space here, very low slopes. We could land there, we could land over here. Right now, since we've got most of the RSL activity coming here, I just put my landing site there. But also I wanted to note that we've also got in that big RSL press release, OJA found the hydrated perchlorate or chlorate signature right here. So it's one of the 4 locations on Mars that they found that. So here's the landing site. It's 2 kilometers beneath the datum here. That sets up our exploration zone. So just more talking about the RSL. The ones in Hale Crater are actually very anomalous to all the other ones in the southern mid-latitudes. It's really the only outlier. This is the seasonality, the time that it takes for an RSL in the typical southern mid-latitudes to lengthen. We've got a little bit of an error bar here. That's this box here where they start lengthening, then they continue to lengthen, and then they stop lengthening somewhere in here. So that's about 100 sols for a typical southern mid-latitude RSL. In Hale, we've got a duration that's 2.7 times longer. We've got a big error bar here because we've got one image here and then another image here, and when we took this image, there were RSL all over the place. So somewhere in between there, but it's at least 270 times longer. What this tells us is the RSLs, according to our theory, the RSL are just waiting to go. There's volatiles that are there in the subsurface. Once it gets over a certain threshold, we start melting those volatiles, and and the RSL start flowing downhill. So our thermophysical modeling indicates a freezing temperature of about 269 to 247 K. So that puts it in the possibly being habitable right now. And so just looking at a cross-section of an RSL, we've got this volatile that's waiting to be discharged in the subsurface. It starts melting, it comes down, and it immediately hits this aquitard. If this aquitard wasn't here, it just goes straight down and it wouldn't go right along the surface. So this aquitard is probably just frozen previous water or salt hydrate that's making an impermeable boundary here. The water's coming down. It's evaporating and sublimating out. It probably freezes at nighttime. The longer it gets, the more evaporation you actually get. And then the scale here is very small. You try to make it as small as possible to really minimize the water that's coming out of here. We're kind of on the order of 10 centimeters here. And again, the slopes of an RSL are 25 to 40 degrees. So 40 degrees, not so good for an astronaut. 25 to 30 degrees, I think would be feasible. So how much water is actually coming out per year? In this paper, we did an estimate of the normal southern mid-latitudes. We found about 1 to 10 cubic meter per meter for the head wall. This is 2.7 times longer, so we just put a greater than sign. We'll have to do some more work on that, but it would definitely be more. So the idea is you just put a French drain, a tile drain in here, a pipe, and just pipe that down. Let Mars do the melting. With this rate, to get 100 metric tons, you only need about 10 to 100 meters of head wall overall. So just to kind of show, here the RSL here in Hale Crater. This head wall right here is 250 meters down. The RSLs are flowing down here. These are these very gentle slopes, well, gentle, being 25 to 30 degrees. This is the bedrock. The RSL are probably coming down here, coming right out of the bedrock here. So 100 meters, and you could get all this water within a year. You're 100 metric tons. On the low side, if our water budget is more right on the low side, on the high side, we only need about 10 meters of that. The big question is how it's getting recharged. We don't like the atmosphere idea because there's just not enough. You just can't squeeze the atmosphere. You can't squeeze enough water out of the atmosphere. We don't really like the aquifer idea either, but at least it's plausible if it's pressurized. And for more on that, I've got a paper in press on this in the discussion. I talk a lot about these two different, what's good, what's bad. So for the resources, get into the ROIs here. You're going to land, you're going to have your resource ROI right next to your landing site, and land as close as you can to an RSL, pipe that in. And then you've also got your material resources. You've got these scree slopes, and if you want to bury your hab, you could probably use that. Going further out, you're going to really disturb some of these RSL by trying to get the water, so you might want to look at the other RSLs around you to look at the more pristine RSLs that maybe you haven't contaminated. There's also gullies in here. There's also really good gullies over here. These are the more typical Malin and Edget gullies. Just try to figure out if these were actually carved by water or CO2. This is just an image showing in that location. Your nice gullies. You could drive up to at least the bottom of these. Look, where was an aquifer here and discharged out to make this, and are there any bug parts in the alluvial fan here? Or is this just all due to CO2 modification? You could set up that and monitor it. Are these gullies possibly, episodically habitable within the last, 5 million years or whatever? So then we've got hydrothermal. There's spectral evidence here showing some clays, other minerals showing, really good hydrothermal activity here on these two rims. We've got good CRISM data there to suggest that. So, yet again, we've got another habitable environment back in the past, right after Hale Crater was formed. Then we've got crater dating. So anytime you're going to go to these places, you really want to calibrate, what the actual data is compared to our Martian, the crater counts. You could get the shock date of Hale, of Argyre, and maybe even into Bond. There's a little pass here of 15 degrees according to the HRC DEM. Probably need to confirm that with higher resolution data. There's also a pass here to go all the way into Argyre if you want. But really the best way to date a crater is to look at the melt pond. And usually you have to drill to do that. You might not actually have to drill to do that. We've got this ponded and pitted material here that's shown in better resolution on a high-rise image here. And you might just be able to date that and figure out what the age of the crater essentially was. Then into the ancient channels. So as I said, you could probably drive into these. There's a lot of this fluvial modified ejecta that happened. You can figure out how much modified ejecta there is. We'd like to do ground penetrating radar to figure out how much ejecta that is. Look at the cross section of that ancient channel to figure out how much water actually did move through there. is this channel going to be deeper than this channel? Was the water flowing all the way from our gyre down, or did you have a source that was going to the north and then another source that was coming to the south? How does this all connect? And so I did my rubric here. I put this as debatable for potential habitability because I'm sure there's somebody out there that is going to debate that RSLs aren't habitable. I tend to think they are, but we can talk. Also, this hail crater has a lot of remnant magnetization around it, but I don't think anyone can tell if there's any outcrops with remnant magnetization on it. And this is so you can see where these are. And then I filled this out. Not a whole lot to say here. I think, just go to the water. Don't need to worry about hydrated minerals or ice. So the highest priority needs, I think we need a high-rise coverage over here. I'll put that in as a high wish. I think we also need to constrain better at the start of the RSLs in this region, which I'm sure Alfred is already going to do. Also, it would be great to get better topography around here to figure out exactly what these slopes are. To study if this is even feasible for astronauts to visit. Is it too steep? Is it not too steep? There's also these passes that I talked about. We probably don't actually need a high-rise DEM. We could probably just figure that out with a CTX DTM. And then also we could get more CTX around here to figure out there's more hydrothermal alteration. So RSL is a resource. This is really the main purpose. I think we need to think about RSLs as a research right now. If we were going to Mars, if we were sending humans to Mars tomorrow, you wouldn't want to go to an RSL site because it's too uncertain. We need more data. We need more mission. We might not get that with our next orbiter, but we may just need a landed mission to really just continuously monitor these through the whole season. And are these slopes too steep? What Grunsfeld actually said in that RSL press conference too was that the slopes of these RSL, an astronaut could walk up to them. So I think an astronaut could walk up there with a little troll, dig 10 centimeters down, put a pipe in the ground, and start flowing this water back down to the HAB. So in conclusion, you want to minimize the infrastructure for water extraction. Hopefully, you minimize the cost and the risk. And with that, I'll take questions during the discussion. Thanks.
All right, excellent. Thank you. Okay, so our last talk in this session, we're going to move to east of Argyre to Noachian Terrace, and the location is a chloride-rich deposit.
Okay, thankfully Matt did Vanna White for me. So those of you who I haven't met yet, my name is Jonathan Hill. I work at Arizona State University with Phil Christensen as a mission planner for the Themis instrument on Mars Odyssey and as a PhD student. And today I'll be introducing you to the Western Noachian Terra chloride deposits. So right up front, what's so special about these particular chloride deposits? Well, they're the closest ones we could identify to previously identified glacier-like forms that occur in the southern mid-latitudes that are also meet the general exploration zone requirements and have potentially traversable terrain between the two. Now, we've already talked a little bit about lineated valley fill, concentric crater fill. Glacier-like forms could be considered to fall into the same basic category. Surface expressions that indicate near subsurface water ice that's undergoing deformation. And as would be expected, we do see other types of those lineated deformation features in the areas surrounding these glacier-like forms. And we've already discussed the values and of having water ice in this form and in these volumes, but what exactly are the chloride deposits bringing to this story? And so the main thing they're bringing is astrobiological preservation potential. Chlorides, and especially halite is a great example here on Earth, are great preservers of all sorts of different biomarkers. These are examples from terrestrial studies, obviously, of preserved cellulose fibers, fluid inclusions, and even actual preserved organics. And current work has shown that these can be preserved for timescales up to tens to hundreds of millions of years. But over the last decade, that date keeps getting progressively pushed back further and further as more work is done. And completely by coincidence, Mark Fries has a poster outside and has set up a nice little show and tell with a nice halite crystal, Permian aged, that has some beautiful fluid inclusions and gas inclusions in them to demonstrate the point. Another thing that these chloride deposits represent is what was potentially a globally spread process in the late Noachian to early Hesperian time periods. There are currently 642 identified unique chloride deposits spread throughout the southern mid-latitudes. And so the hope is that by studying these particular chloride sites in our exploration zone, we could then extrapolate that information to the other chloride deposits and try to work out a consistent story about what is this telling us? What are these evaporite mineral deposits telling us about what Mars was doing at that critical time when the Valley Network formation was kind of coming to an end? There was a last gasp of liquid water on the surface. So zooming in a little bit here, this is the exploration zone. And to give a little context, as Matt said, it's just to the northeast of Argyre. And zooming in a little bit closer, we see the exploration zone in more detail with mole topography. The chloride deposits are located very near the landing area, which is in the center of this exploration zone. And the other main feature I'll point out to you is this large outflow channel that kind of goes up toward the top of the EZ. And the much smaller side channel that sort of drains off of that larger channel would have ponded in this area until this wall may have been a very old crater breached and drained it. And so we think that's where you enabled the chlorides to evaporate in different time periods and collect. And this is at a lower elevation than that outlet. So even once that wall was breached, you still would have had ponding and evaporation of fluids. So these are the exploration science ROIs and resource ROIs that we identified, and so we'll step through those fairly quickly. To start out, the science ROIs. Science ROI 1 is the primary chloride deposit that's located closest to the landing site, only 10 to 12 kilometers. And this is an image of it with Themis DCS 875, which shows that the chloride's in a nice, distinctive, almost diagnostic light blue color. And unlike other chloride deposits, such as the Margarita Frontera ones, these actually seem to lie on top of volcanic units. In this case, a basaltic unit with approximately 15% olivine abundance. We don't have great chrism coverage over these, but based on what we do have and what we see at other chloride deposits around the globe, we expect to see phyllosilicates and possibly some hydrated minerals. Now, luckily, that's not the only chloride deposit that we have in this exploration zone. We have two others that are sort of progressively further from the landing site, so they'd be progressively harder to reach. Chloride site deposit 2 is actually slightly bigger, so it would offer more material, and also seems to overlie an olivine-rich basaltic unit, which I should mention, these basaltic units look like they're clearly younger than the bulk Noachian terrain that they're lying in. And so they'd hopefully provide a datable surface that's separate from the Noachian highlands. And finally, the third chloride deposit that we're looking at, it's much smaller, has a lot of different characteristics than the other ones. And so one of the testable hypotheses we could have is whether or not these chloride deposits are actually directly related. Do they share the same formation mechanisms, or are they the result of completely different processes, potentially at different times? And so that could inform how all those other 642 chloride deposits around the planet were forming. Is it a consistent process, or are there multiple processes involved? So moving on a little bit, Science ROI 4. This is the area that I pointed out initially as having the glacier-like forms. But our main interest in this region is the gullies and the potential for RSL. And this is a great environment to be presenting this in, because I simply had this listed as a potential RSL. Based on the morphology of that crater rim, it looks similar to RSL slopes, but had not seen any confirmed or even candidate RSL numbers over that area. But just from the last presentation, it looked like there was a potential ROI blue dot lying right on top of this. So I'd be interested to see where that came from. But either way, I think we're covered. If there is an RSL, you can argue, as some will and some won't, that that would give you access to potentially habitable environment. But we think if it's not an RSL, it might actually even be more valuable, because if it's not an active RSL, it could give us access to basically an RSL analog on the surface of Mars that we could investigate without the planetary protection restrictions that would have to be changed or just violated in order to reach some of the others that are currently active. So science ROIs 5, 6, and 7, this is sort of a group of ROIs meant to sample materials from different time periods. As you can see from this overlay of the Tanaka map, this exploration zone covers both early, middle, and late Noachian highlands units. And so we take advantage of that and try to sample all three. I should say that based on the resolution of the data we currently have, we've picked out what we think are the best areas to do that sampling. But with higher resolution data, these, especially these two out here, 6 and 7, will very likely move around. Number 5 is actually really easy because this actually is underneath part of the landing site that we selected. This part over here is part of the landing area. High thermal inertia region, probably very rocky. It's probably a good place to pick up those materials. Further out, ROI 6, this is where we would hopefully get early Noachian material. Again, slightly higher thermal inertia is what led us to believe this might be a good area, but higher resolution data might point us at actual outcrops that we could use. And one of the interesting things here is that this does have a remnant negative magnetic field based on the MGS Mag-ER measurements. And then finally, science ROI 7, this is where we would acquire the late Noachian material. And this area is interesting because it also contains a remnant magnetic field from the Mag-ER data, but it's a positive measurement. And so hopefully by collecting material that's from 2 different magnetic regimes, that would sort of add to give us 2 data points to look at and try to work out what the remnant magnetic field is trying to tell us. And finally, at Science ROI 8, the channel stratigraphy. This is the channel leading out of that basin where that main chloride deposit formed. And on the north side, there's still some rather steep walls there that we would hope still have some exposed stratigraphy, give us a little further look back in time without having to drill down or anything like that. And the traversability down this canyon actually looks like it might be fairly easy, although we'll need higher resolution data to know that for sure. And now quickly to go through the resource ROIs that we've identified. The first one is in the same crater as those initial glacier-like deposits and gullies. And this is sort of typical pasted terrain. For those who aren't familiar, this is also another kind of like lineated valley fill and concentric crater fill. It's another form that we see on the surface that's indicating that there's near surface water ice. In this case, not really undergoing that much deformation, but it could provide a rather large supply of water. This area does have an accessibility concern, obviously being on the slope of this crater. Luckily, the rim is irregular in this area. So the deposits and patches that are up close, they have lower slopes that you could need to go over to access them, and accessibility would go increasingly difficult as you go down the slope. So in an attempt to sort of mitigate the problems associated with that access problem, we have resource ROI 2, which appears to be an example of lineated valley fill in the crater ejecta just outside that rim. So ROI 1 is right in this area here. Now, at the very limit of the CTX coverage that we currently have of this area, we look like we can convince ourselves we're seeing very stereotypical lineated valley fill structure in that channel. But that's a very tentative identification. The data is not that high resolution. And so this will actually factor in later. It's fairly high on our list of prioritized observations we like to get. Because if we can move the water resource closer and closer to the landing site, the better. So science or resource ROI 3, what we're calling lineated crater fill. I'm not sure if that's a real term people have used before. It is very similar to what you'd expect of concentric crater fill, but since it does not go around the crater and has some breaks in it, I think that's why you're not getting the truly concentric forms. But still, you're getting almost sort of lobate debris apron type lineations to it. And again, this would be a significant water resource. This does have also much more serious accessibility concerns because really the only possible probable path down into the base would be to come all the way down here. That's a really long traverse. But because it is such a huge potential resource, we wanted to call it out and give some bright engineer who's probably Alex's age right now the opportunity to eventually develop some way to access that. And I should mention that there are Chloride profiles over this deposit, and I don't know if they've been analyzed. We don't have in our group experience analyzing those. So Jeff, wherever you are, we'll probably be contacting you shortly for maybe some assistance on that. So resource ROI 4, Olivine-Bearing Basalt. As I said before, the volcanic basaltic units that underlie these chloride deposits are much larger than the chloride deposits. That's Science ROI 1 there, the little chloride deposit, a couple little outlier chloride deposits. But then the main mass there is just an olivine-rich basalt. According to the test spectra, we're looking at about 15% olivine abundance, but we haven't really pinned down what the phone number might be or what range it might be in yet. But either way, it should provide a decent feedstock for iron and magnesium. And in high rise, you can see that surface is actually broken up quite a bit. There's lots of cobbles and such on it. So a little bit of a trafficability problem, but if you just start mining that material from the edge and work your way in, you can build yourself a path. And finally, resource ROI 5, Silica-Enriched Material. This is within ROI 4. It's an area that sort of shows up as a greenish color in the Themis DCS 875 images. And according to the test spectra, we're getting a 25% or greater abundance of a high silica material. We're a little confused by it. We haven't been able to go too far with it yet. And we're not sure if that's an alteration product or if we're looking at some sort of hydrothermal system associated with these, what appear to be much later than Noachian eruptions of volcanic basaltic material. Okay, so I won't bore you with too much about the science rubrics, but the short story is we think that basically this exploration zone fills out or almost fills out most of these requirements. There's some that we don't meet. For example, we don't think we have a realistic way right now for our site for assessing trace gas sources, and we don't have any large structural features, faulting, or anything like that running to this ROI or EZ. And similar story with the resource ROIs. We think we meet or potentially meet most of these, except for things like we're not located in the northern hemisphere. We're actually quite far from it, down at -37, and again, we're not a low latitude. So our highest priority data needs for science, we're going to be looking for high-rise and CRISM FRT pair of Science ROI 1, that main chloride deposit, so we can assess the quality of that deposit and verify that we have our stratigraphy that we're assuming right now is correct. And then for resources, we'd like to have a CTX stereo pair of the traverse route between the landing site and resource ROIs 1 and 2 to really try to pin down whether that is definitely traversable. And then for potential future assets for science, we would love to have a thermal IR spectroscopy capability past 25 microns. That's when you can get out and actually see the really good absorption bands in these chlorides. You can differentiate the chlorides from one another. You can get absolute abundances. You can do lots of great things that you can't do with sub 25 micron data. And then echo what's been said multiple times, high resolution, shallow subsurface radar would obviously inform if there is any liquid or water ice deposits that are even closer to the landing and habitation sites. And so in summary, we have the chloride deposits that are remnants of potentially habitable environments that also have very high astrobiological preservation potential. We have near-surface water ice that offers a significant resource, as well as some really unique Amazonian climate science that can be done. And then additional ROIs representing a variety of other science and resource targets. And with that, I will turn it back to Matt.
All right, I think we need speakers up front.
Yep.
Okay, so we're going to end this at 1 o'clock so people have lunch, and I just want to emphasize we're going to start at 2:15 sharp on the next session. So try, that's pushing a little bit for if you're leaving site, but we really are short on time given the other activities that are going on tonight. So we'll get as many questions as we can. There's a lot of common themes, and you'll have access to everybody later on, of course. Okay, with no more ado, any questions over there? Can we get a mic over there, Kevin? And please introduce yourself, just to remind everybody. No, you're not.
I'm gonna just.
No, we need you to be hot mic so Nikolai can hear it too. Nikolai, are you there?
Yep.
Great, thank you. And feel free to chime in if I don't call on you.
Okay, this is a comment about the RSLs and the issues related to their origin. I think a pressurized aquifer, as much of a fan of aquifers as I am, the idea that aquifers would preferentially discharge at high elevations hydraulically doesn't seem to make, isn't the most logical expectation. You would expect that a pressurized aquifer, if it had any kind of extent, would discharge to lower elevations. And since we don't see any RSLs there, it might be argued that these aquifers are not discharging, or that they're not aquifers that are supplying the water. It seems far more logical, I think, that RSLs result from some sort of surface process, whether it's the melting of near-surface ice, some processes involving exchange of the atmosphere with the surface. That might well explain their occurrence at high elevations. But those conditions could also exist on horizontal surfaces at low elevations, and we don't see them simply because they don't result in any movement down a slope. That may be the thing that enables high-rise to detect the occurrence of these brines. The most effective way to determine the occurrence of these brines and whether there is a preferential orientation or distribution of these on slopes versus horizontal surfaces is by far the high-resolution imaging kind of radar that's been proposed for 2022. This was something that was identified as the most efficient way of recognizing these kind of features by PrevCom a number of years ago. And I really hope that this kind of investigation does occur on the 2022 orbiter.
Any comments?
Yeah, so I'm a big fan of radar. I think we should do it for sure. Back to the pressurized aquifer idea. We only see RSL coming out where we have bedrock or big rocks. And so I think there's something there with the thermal conductivity of that bedrock, that solidified unit, is getting heat into the subsurface. So I think the idea is that we have basically an ice dam pretty much everywhere, and that the only place this aquifer is able to reach the surface is by melting out that ice dam and allowing this water from below to come out. Atmospheric, we would love an atmospheric answer to this, especially since we've got 200 sites now. Yeah, do we really have aquifers over the entire planet? That's crazy. Yeah, but the water budgets that we're coming up with, I mean these things are going for 200 meters in places, and they're about a meter wide, and you just figure out back of the envelope with the porosity 30%. That's a lot of water that's in there. And how do you get that out of 10 precipitable microns in the atmosphere? It's really hard.
Okay, next question. Alfred.
Alfred McEwen. A couple of comments. First, Steve, if deliquescence is happening on flat patches, it should create a darkening, at least in the morning when it's more stable. So Trace Gas Orbiter is launching in a few months, and Cassis is 4.6 meters per pixel. That's probably good enough. We can observe. It's an inclined orbit, so we observe at different times of day. So we'll be looking for any anomalous dark patches in the morning, so maybe we can get an answer to that question. Another comment about hail crater. Colin Dundas sent me an email yesterday showing gullies on the outer rim that are active. There are significant changes in the channel and the deposits that he just found. So I don't think anyone else has suggested a site with active gullies, so that's something of interest.
Thanks.
Okay. Any?
Hail.
Okay. Alex. Alex is next.
Alex Longo of the Cardinal Gibbons High School. I think that it's important to have a conversation about how best to prove the existence of these glaciers and what their coverings are, how deep below the surface the ice starts. I'm not sure that this workshop is the best place to have it, but I think we should just start discussing if a rover would be the best, if an orbital instrument would be the best, if some sort of penetrator dropped from orbit would be the best.
And you guys want to take it?
Yeah, so you can start to get at that with Charade, but as Jeff pointed out the other day, the resolution of Charade means you can only analyze these really large deposits, and the ROI 1 and 2 that we have on our site are rather small, and so I don't think Charade is useful in that case. And that's where potential follow-on instruments like we keep bringing up, higher resolution shallow radar would be helpful, or if you're actually on the ground and can do some sort of ground-based penetrating radar, that would actually be ideal, of course. But
I mean, the problem with the high resolution radar is it's high frequency, and you've got at least a meter of rocks above that's going to scatter a lot of that information away. So it might be best to do it via a rover-based radar. But yeah, we'll just have to see what the specs of that high frequency radar is.
Okay, and Nicola, do you have anything you want to add to that conversation? Nikolai.
I can say that glaciers which are in between escarpments are also relatively shallow compared to those in the terminus, and it's probably because they are a little bit towards the south. But they are huge still, so maybe I didn't look to shower data on this location, so maybe Charade can still see the ice there. I don't know.
Okay, thank you. Another question. Right here, if I could.
Drew Levy, University of Texas. It seems like the search for water on Mars has led us to salt, ice, and minerals, and we know kind of more about the latter two than the first one. Can you comment on the nature of the salt deposits geologically? Are they, or the chloride deposits in particular, are they vug filling? Are they, playa floors? Where is the salt, and why is it still there after all these years?
Yeah, so the ones that we have identified and have high-rise coverage over, you do see usually sort of the playa-type polygonally fractured structure to them. That's only in the best cases, though. There's actually a wide range of surface morphologies that we've seen. Others have sort of ripples in them. And in terms of preservation, many of the other ones that have previously been proposed, like the Margarita site that was proposed for the 2020 rover, that actually has a volcanic capping unit on top of it that has been eroded away. And in this case, you're seeing the chlorides through either erosional windows or the edges of that erosion as it goes back. We think in this case, in the Noachian Terra, you're actually seeing the opposite. You actually have chlorides that have formed on top of a volcanic unit and are somewhat easily being stripped away. And so the first chloride site in particular, you can see where toward the edges it's getting frayed. It's only in the low points. And so that's why one of our highest priority observations is to get some high-res coverage to confirm that we really do understand the stratigraphy of that correctly. So I think in short, there's a wide range of areas and stratigraphies involving these chloride sites that hasn't been fully understood yet.
Okay, and then can you guys move a little closer just so our online audience can see it? Thank you. I'm sorry to have to keep doing that. And then we're going to John Grant, and then I would like, there was someone who was asking a planetary protection question in the previous session. If you want to ask the question again, somehow flag it to me, because we have this interesting new wrinkle of the RSLs coming in here, so it's a good segue, if we can, to that important topic. So, John, over to you.
I wanted to follow up on the stratigraphy of these chloride deposits. I guess my familiarity through the Osterloo et al. Paper and the landing site for robotics process, I thought these things were all really quite ancient, but the relationship you showed and just commented on, that in Noachian they appear to sit on top of these basalts, which you commented are younger than the Noachian plains suggests that there's quite a range in ages. Can you say something about what you think that relationship might be?
Well, I just said that those volcanic deposits that the chlorides are sitting on are obviously younger than the surrounding Noachian terrain, which is sort of middle Noachian in age. It could be, middle Noachian minus 1 year. We haven't done the crater age dating, but it should be a datable surface, and so hopefully within the next couple months we'll have crater age dates on those surfaces. At least 1 or 2 of them might be big enough.
Okay, and did someone have I guess, well, if you have the planetary protection, just let me know. Any other questions for this panel? Okay, not seeing any. So if you are, wave your hand because it's very bright up here. Okay, so what we'll do then is we will break now for lunch. Be here, please, at 2:15. I'm a bit of a taskmaster on the schedule. Ben's even more so than me. So.